Okay, so the first question is why did I want to give this presentation? I put it together like a month or two ago for DC 404. It's like the local DEF CON group in Atlanta. And I put it together because someone the month before gave a talk on incident response. And incident response is a thing that I was doing for a bit, now I do malware analysis, so I was kind of interested in the topic. So he gave a really cool presentation about different like network forensic stuff. But every time he got near malware analysis, he kind of was like, we're not going to talk about that. So afterwards I asked him why. He goes, well, assembly is kind of just like, ugh. And it's a thing that I hear a lot. People kind of have that reaction towards assembly. And I really don't think it's that bad. So the idea of this presentation was to, again, convince people of DC 404 of that. So for the presentation, I wanted to go through a couple of things. The first one was, what is assembly language? Probably a logical first question. Also, why is it worth knowing? Then we'll go into some like basic I guess, points of how it works. So basic computer architecture, x86 assembly fundamentals, like registers, instructions, and memory. And then if you're so inclined, where you can go from there. Oh, we're getting there.
All right.
Okay, so this slide, 3, 2, 1, boom. Okay, so that was what is the presentation. So this is what isn't the presentation. As you can see, it's not an inclusive list of things that it's not, but just a couple that I wanted to highlight. It's not an x86 assembly masterclass for a couple reasons. One, I only have about 45 minutes, but two, even if I had all the time in the world, I'm not the one to teach a masterclass because I don't know everything there is to know, or even most of it. And two, this isn't a malware analysis presentation. So I had this in the slide for DC 404 because I initially said I was going to do a malware analysis presentation, but no one knew assembly, so I figured I'd step back first. Conveniently, I am doing a malware analysis presentation directly after this one. So if that annoys you, don't worry, it's coming. So the logical first question again is, what is assembly language? So I've got this little scene to play out here. This is you, or it's me, it's one of the two of us. You just got a shiny new cool computer, right? And your shiny new cool computer has an Intel processor. Maybe it has a processor that isn't Intel, but for today we're going to go with an Intel processor. And your processor is really, really cool, right? So you want to show all your friends how cool your new computer is. I hope this is how you guys live, because this is how. And you write some sweet C code for it. So it's a little small, and maybe like I'm directly blocking you, sorry. But you write some sweet C code, hello world. So you get all excited, you've written some code, you've got a new cool computer, and you want to show all your friends how cool it is. Unfortunately, your Intel processor does not run C. You cannot just give that to your processor and have it run it, right? So this is where compilers come in. So fortunately, there's a compiler made specifically for the type of processor you have. You can give it your C code, it takes it, and it does a bunch of stuff to interact with the processor so that you can run it directly. So again, this text is really small. It's not actually supposed to be read. It's just the output of file on the binary library. So it says a couple specific things. It's an L32-bit LSB executable, Intel 8386 version 1, sysv, dynamically linked, all this stuff. Basically saying this is made specifically for your processor, or the type of processor that you have. So once it's in that state, you can execute your program. So you do it in order to show all of your friends how cool you are. So you run your program, it says hello world, and all your friends are stoked, everyone's excited. Good job, really, really cool. But the question is, what actually makes it work? So if you were to peer inside your binary, you see something like this up here. And I've put each thing on its own line for readability's sake. Some might argue it's still not very readable. But this is what's inside your binary. It's just a bunch of bits and bytes. And here we've represented it as hex. So full disclosure, this isn't the whole binary, this is the main function. But this is actually what it is. And this is exactly where assembly comes in. Because all of those things translate directly to assembly instructions. So again, this is where assembly language kind of comes in the chain. So assembly language is those bits and bytes represented in hex, which makes up the binary, which makes the code that you can run. So that's what x86 assembly is. So a very logical second question. Why do you care if compilers are a thing and they can do all of this for you? That's a very good question. And I've got, I think, 3 reasons for you, maybe 2.5, I'll say. So the first reason is that you can, it helps you to write better code, or at least understand it a bit better. So to explain what I mean by that, first I just want to make this concept clear on that lovely blue on blue slide. It looks great on my Retina display, I'll have you know. So I imagine a lot of people are kind of familiar with this as a concept, but just to make it clear, we've got this notion of low level and high level. So assembly is what we call a low level language. But it works kind of backwards from how real life does. In that in real life, low level means typically less complex, right? So Math 101 is a low-level course. Math 201, a bit more complex, a higher-level course. Math 301, the land of geniuses, right? It's the highest level course in my example. It's high level because it's complex. So the higher level something is, the more advanced it is. But that is almost the complete opposite in terms of tech. So the higher level something is in tech, or at least in context of a computer language, the more abstracted it is from what the processor is actually doing. So as an example, I have Python as my highest level language. And the thing is that Python is kind of like a playground in that you can do basically anything you want without having to worry about how the OS actually deals with what you're doing. And I don't say that to like talk badly about Python. That's awesome. Most of the code I write is in Python. And the thing is that it's very abstracted. So C is a bit lower level. And it's not because it's less advanced or less complex. Some might argue the opposite. But the thing is, it's less abstracted than Python. So you will deal with some things like pointers directly, but there's also still a lot happening that you're not directly in control of. And again, you can see that because of the fact that you use a compiler, right? You give it a C instruction, or a C instruction, I'm not sure if that's what you call them in C, and the compiler takes it and says, okay, here's what it needs to do for your particular processor, and puts it together. And then below that still is assembly. So I say not with an asterisk because I'm really scared of like absolute statements. But there's very little abstraction, if any. And we'll see all about that. But that lack of abstraction is what makes assembly a low-level language. So as a side note, people who know assembly like to refer to languages like C as high level. So if you learn assembly, you get to do that too and impress all your friends because they'll think that's really cool. Don't do that. People don't think that. So to bring back this slide from a couple of minutes ago, why? Because it'll help you write better code, or at least understand it a bit better. So even if you're not actively writing assembly, which I wager that most people who know assembly don't, it'll kind of give you a better understanding of what your higher level code is doing. So when you've seen how things like pointers work or data types work at an assembly level, it kind of makes it much easier to understand what's happening under the covers when you're writing Python or assembly, or Python or C or whatever language you do. Additionally, your errors will end up making more sense. And I say that because when you've got some kind of fault that happens, typically it gives you some kind of low-level message, and if you're familiar with assembly, that will again make a fair bit more sense. So, everyone's okay? Cool. So this for me is the biggest reason, and I say it's a whole new world of code that you can read when you know assembly. So reverse engineering things I think is kind of cool, but the problem is that typically you're not reverse engineering open source documented code. Sometimes you are, and I'm not going to say that's easy. But a lot of times it's compiled binaries that you're trying to dig into. And being able to disassemble that code is awesome because you can take that binary, which is for a lot of people like basically a black box. You can't really get into it, but you can take that and see exactly how it works. So you can do things like malware analysis, which is probably the best thing you can do, in my unbiased opinion. Or exploit development, or reading closed source code to extend it, whatever. If you can read into like a closed binary, there's a lot of cool things that you can do that you otherwise couldn't. Additionally, I think sometimes it's worth reverse engineering your own code as well. People don't think about it, but when you've written code, you think you know what it does. I disagree. I think you know what you wrote it to do, but you don't necessarily know what it does. And disassembling your own code can kind of help you see what's actually going on under the covers, and it can be kind of cool. So you don't have to read line by line here. You can, you don't have to. And I'll talk about this exact example in the next presentation. But I just wanted to show like a real world example of where knowing assembly came out to be something genuinely useful. So this was from a particular piece of malware, and typically I explain it more here, but I guess that's spoilers for the next presentation, which is directly after, so we'll wait. But by reverse engineering this block of code, we were able to predict the actions of a particular problematic piece of malware to reproduce it and effectively help prevent it for people who had this information. So cliffhanger, if you want to know what that was, stick around. Or just Google the presentation I gave last time. So the last reason, and this is the one I call the half reason, because for me it's not a big one, for me at least personally. So you can write assembly. So does anyone here know assembly? Any assembly? Okay, a bunch of waggly hands. Does anyone actively write assembly from scratch? No. So admittedly, it's not a huge sample size, but a lot of people who know assembly generally don't write it out by hand a lot. The example, or the exception, I guess, is shellcode, which someone was kind enough to bring up to me like 2 days ago as a thing, because I don't do a lot of shellcode. But it's a cool thing, so You can write assembly if you've learned it, but again, it's not really the major reason that I'd push. So, okay, at this point we'll get started, I guess. Does anyone have any questions up to this point? I'll break a couple times.
Wait, yeah. Yeah, you haven't differentiated between assembly and machine code. And those two are two terms that get thrown around a lot that mean different things. It seems like you call one thing machine code that's actually, or assembly that's actually machine code.
We'll get there. I'll differentiate between the two.
Okay.
Thank you. Yeah, that'll come in just a little bit when I talk about instructions, what actually makes up assembly. So, okay, I just wanted to bring back this slide from a little bit earlier to talk about what actually distinguishes learning assembly from having to learn other languages. So like I was saying here, assembly is a very, very low-level language. So what does it mean you have to learn a low-level language? You can apply the same thing to learning C after coming from Python or whatever. And that is the fact that when you have a language that doesn't have abstraction, you have to learn what is generally abstracted in the other languages that you generally use. So the first part of learning assembly is learning those things that you don't generally have to deal with. So the first thing that we're going to talk about is not actually going to be any assembly instructions, which we will get to. So what's abstracted out of those other languages that we have to deal with here are the exact workings of your processor. So again, today we're going to be talking about the Intel 32-bit. And this is the Intel 32-bit and 64-bit architecture manual. It's a really good tome, I guess, to have if you're interested in getting into assembly. But I show you this for a couple reasons. One, that's actually page 1 out of 3,439. To be fair, there's also 64-bit stuff in here, but it's still not a short thing. And again, I show you that for two reasons. The first is, I guess it's a fantastic resource as you learn and are going through things. It's kind of like your man pages, right? This has a great reference of all sorts of different instructions, how different registers work. Pretty much anything you need to know can be found in here, and it's really not that bad to read. Not like cover to cover, but if you have questions about particular things, you can get good info. And two, to show you how much there is to learn. So again, this is page 1 out of 3,439. I have not read all of it. I do not know all of it, but I can still be functional, right? And that's kind of what I'm looking to show. You don't have to be like a wizard to kind of get and be able to be functional with assembly language, specifically Intel 32-bit x86. So, okay, what we are going to be talking about first are processors, right? Because we need to have some kind of foundation before we dive into the instructions. So earlier I showed you a disassembled version of my Hello World program. And it broke down to a series of instructions in assembly. The instructions are run through this, which is my processor. Can you guys see the distinction between the shape and the background? I mean, it's a square. This one's not too complex, so we should be all right. So the instructions are run through here, the processor, which actually does the things. That's the scientific term for what a processor does. And it has a few components inside that make it happen, and 3 of them are components that we'll discuss. The first one is the ALU, or the arithmetic logic unit. Okay. The ALU, or the arithmetic logic unit. And this is where the actual instructions are processed for the logic that happens. The instructions that we write will be going right through here, so we'd like to know about it. But we don't have to know too specifically. What we want to know is that this is where the logic actually occurs. So if you've ever taken like a logic course, and we were talking about gates earlier, this is where gates exist to get you back the results of the instructions that you'd like to run. And if the processor is the thing that does things, this is the doer of that. To speak in no minced terms. So the second part we'll talk about is the control unit. And this is one that we won't have to go too far into, but it's good to know that it exists. So like imagine you've got a 5 CD changer, which was a thing at some point. You've got 5 CDs in there, and you'd like to play a song. You tell your 5 CD changer what song you'd like to play on what CD. So it has to switch around the different CDs until it finds the right one, and then it sends the contents of that to whatever part of the CD player plays the music. That's kind of like what the control unit is. It gets your instruction and then decides what it has to be broken up into, what values have to be fetched, what logical operations to do. So again, the things that we put into the processor will go through here, but you don't have to know too much more about this specifically. But again, it's worth knowing. And the last part of the processor that we'll talk about in depth are the registers. And I've got like a whole section dedicated to registers, so I won't talk about it too much now. But this is kind of like your working space here. Yeah, for now we'll leave it at working space inside your processor. And these will be very, very, very important. But again, we will get into it more in depth in just a little bit. So this is my to-scale accurate diagram of a computer. And we are going to step out of the assembly line. I have a huge processor. So we're going to step out of assembly line for a moment. So when you've gotten a program that you've written, something you've compiled, you're not just running it in memory, spoilers, I guess. It typically sits on your hard drive for storage. It does that because storage is cheap, relatively cheap. It's plentiful, which is kind of what we mean by cheap. And it's persistent. When you shut down, hopefully what's on your storage stays there. But when we execute a binary, we don't run it from our hard drive, right? I guess we could, but it would be super slow. That's where memory or RAM comes in. So memory, when compared to storage, is a lot faster. Accessing it to do rewrites are significantly cheaper. But the thing is, it's a lot more limited in quantity, than space is on a hard drive. So we use it when we need to. We don't always need to, but we use it when we do need to. So we've got a bunch of stuff in storage. When we want to execute a program, we load either all of it or pieces of it into memory to execute it from there due to speed. So this is where registers come in. So again, registers sit on the CPU. They're part of the CPU. And registers are to memory. This is a rough comparison, I guess. Registers are to memory what memory is to storage. In that registers, even compared to memory, and like astronomically so compared to storage, are very, 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 very limited in how much of them we can use. So we'll talk about specific registers in a moment. But just to give you an idea, when we talk about registers, we don't talk about them in gigs or megs or even bytes. We talk about them in bits. At least, again, in Intel 32-bit assembly. But even compared to memory, they are significantly cheaper to access for speed time. So we like to use them as much as possible to keep our, program running well. And because this architecture actually demands it, which we'll get into as well. So what I'd like to do is show you off some of the structure of a register. So this register is called EAX. We'll get into some of the different registers and how they work in a little bit, but I just wanted to use this as an example. So up at the top, I have a little size chart. All the way at the right is 0, 8, 16, 24, and then 32 isn't there, but the total thing is 32-bit size. So in Intel 32-bit assembly, the size of a register like this is 32 bits, or 4 bytes. And I'll talk about exceptions in a little while. So again, EAX is one of those general purpose registers, and it can hold anything that we can fit into it. The thing is that it doesn't exactly know what it's holding, but anything that we can fit into 32 bits can go into this EAX register to be accessed for whatever we'd like to do with it. And when you read from EAX, you get 32 bits out. But we can also break it up into a smaller part. So EAX is 32 bits, AX is 16. So a little bit of trivia for you. I didn't actually know this at first. E in EAX stands for extended, because before 32-bit processors, there were 16-bit processors. I was not doing assembly at that point. I was not doing much at that point, but we had them. So AX, compared to AX, does a couple of cool things. For one, it makes processors kind of backwards compatible, because you can write a program referencing just AX, BX, CX. And as far as I'm aware, it should work out pretty all right, because it can all be accessed the same way. But also, sometimes you only like to access the lower half of a register. And that's where referring to one like this comes in. So AX will get us the first 16 bits, where EAX gets us all of it. When I say first, I mean the lower half. So the problem here is that we cannot address directly the second half or the top half in the same fashion. There are ways you can do it through certain types of logic, but there's no like a other letter, because it doesn't exist. You cannot address that top half directly. So we can break up some of the registers one more time. And I'll clarify which ones, but for the sake of today's presentation, I think that was a bit much of the fire hose. So some of our registers can be broken up this way, but not all of them. Anyway, for the some that can, we can break up the bottom half one more time. So we can then do again AL for A lower or AH. So AL gets us the first byte, or 8 bits, whereas AH gets us the second one. And just like referring to a register as AX, we cannot directly access the top half of a register in this fashion. So where here I have EAX, AX, AHAL, the register called EBX would be EBX, BX, BH, and BL. So most of the register names kind of make sense in that fashion. So we've got a couple that we can deal with, fortunately. You can kind of say the more the merrier when you know how they work and you're ready to use assembly, but for the sake of learning, I guess we kind of do have a fair amount to remember. So these are what are called the general purpose registers. So I'm going to caveat this statement in a second, but any of these can be basically used for anything that you like to use them with. That said, if what you want to get into is like reverse engineering or writing code that works with other code, which is, I guess, a good thing, there are certain practices that compilers follow. So while you can't use any of these for anything that you can fit into them, you'll see certain things happen when you're looking at compiled code just because of the fact that they're written kind of like a spec or a code. And I'll talk about a couple of them now. I'm not going to talk about EBX or EBX right now. I'm just going to describe EAX and ECX, two different general purpose registers. So EAX is what I have labeled as the return value, and this is straight out of that 3,439 page manual from earlier. So in assembly, when you return things, it doesn't work like a lot of higher level code. In C or Python, and I keep saying those because those are the languages that I know, typically what happens is you say return and you get a value that you'd like to return. In assembly, the return instruction doesn't actually pass a value. That's because what you're supposed to do in assembly is leave whatever value you'd like to return in EAX. So you can also use it for other things like different types of calculations. But one of the things, like if you're trying to reverse engineer code and you see a function return, and you're looking for the results, EAX is the place to look. Additionally, I want to clarify ECX a bit, because I call it the ASM counter, and this isn't actually the name out of the manual. The manual calls it, I think, the loop counter. But I wanted to clarify, because again, in higher level languages, when we think of loops, we think of things like, for loops. That's not necessarily what this counter is used for. There are some instructions that the logic of them that's like hard-coded into them requires that they loop a certain amount of times. And they look at ECX as their counter. So when I say the ASM counter, I mean the counter for those types of instructions.
Would this also be referred to as the PC counter, or is that different still?
I'm not familiar with the
Like
PC counter.
where in memory you are, like at a certain specific spot.
Oh, that's a different, like you mean the instruction pointer.
Yeah.
That's a different thing.
Okay.
Yeah, I'll talk about that in a moment. Yeah, so this is the, ECX is the ASM counter for particular instructions that loop automatically. Then there's a couple more general registers that have specific uses. So ESI is the source index, and EDI is the destination index. So typically, if you're looking to move a bulk of data from one place to another, you keep pointers of where you have to take it from and where you want to put it to. And you'll see ESI and EDI used in this fashion. The important ones to know out of these, though, are ESP, the stack pointer, and EDP, the base pointer. It's a little fire hosey, but these are the last general use registers that I'll describe in detail. So the stack pointer points to the top of your stack. Are people familiar with the stack as a concept? Is anyone not? It's cool if you're not. Okay. So I'll talk about the stack a bit more, but just for some context here. The stack is an object in memory that allows you to place values onto it and take them off of it. So it's a structure that you need to kind of keep track of, or the computer generally keeps track of for you. So it's important in assembly, and I'll explain it more in a minute, but just for some context here. So ESP, the stack pointer, points to the top of it, and the base pointer points to the base of the part of the stack that you're using at the time. And I'll explain all of that more in a minute. So we're almost done with the register part. Again, it's a lot all at once if this is your first time exposed to assembly. Actually, I'm going to take a footnote there. I took a C course in school, and I was fortunate because it made a lot of sense. And it made a lot of sense for me because I had some C experience prior. And again, this is a footnote from this, because I had some experience prior. I didn't know C very well before this course, but I'd heard of things like variables. I'd heard of things like pointers. So then when someone came back around and actually explained them, they had a place to go in my head, right? So the first time I learned them, I didn't learn them very well, but it made actually hearing them taught so much easier. So one of the goals I have today is not to, I don't know if anyone saw the blurb that was online, but it's not to teach you assembly in an hour, because not only can I not do it, but I suggest it can't be done. But the idea is to expose you to these terms. So if you do decide to pursue and you hear about a register, oh, okay, I have a place to put that in my head. So if you haven't memorized all of these registers yet, it's cool. That's not really the goal. So just know that. So a couple more registers that I'd like to talk about. The first one is EIP, and this is what, I'm sorry, I don't know your name, you were kind of referring to a moment ago. So EIP is the instruction pointer. So I'm not sure if anyone here plays around with like binary exploitation or capture the flag challenges. You'll very frequently hear people refer to EIP, or like, I got EIP. And as such, I figured there'd be a really funny image about that. But I searched, I wager almost the entire internet, and I didn't find it. So if you've got one, please, I'd love to see it. Anyway, what EIP does, the instruction pointer, points to the next instruction that your processor should execute. So it kind of maintains your state of where you're moving through the binary. So if you can change what is contained in EIP, you can change what the program executes. So when people try to write exploits for code, and they want to run their own code execution, they try to control what's in EIP. You won't typically have to deal with that directly too much, but I'll explain some cases where you will. And then just in case that wasn't enough, check this out. This is what's called the E-flags register. This is probably the most funky, to again use the technical term, out of all of them, because it's not used like any of the other ones. The E-flags register works bit by bit. It's not one that we directly read to or write from, but these different bits do different things to maintain status, settings, or results of prior instructions. So I'm not going to go into all of them. I will go into a few in just a little bit, but you should definitely have heard of the E-flags register. And the last set of registers I'm going to talk about, again, we've got a couple of them. They're called the segment registers. So like I said earlier, when you run a binary from your hard drive, it gets loaded into memory. And a binary has different parts that aren't necessarily, a binary has different parts. Specifically, you have a code segment, a data segment, and a stack segment. These aren't all parts of the binary, but they're parts of regions in memory that your binary uses. So these segment registers, the top, CS for code segment, DS for data segment, and SS for stack segment, are effectively pointers to the bottom of those portions. So if you'd like to interact with some data that you have in the data segment, instead of having to know the real address of it, you can say the data segment plus the offset of where my data is stored. So that's where you'll see those. The bottom three, ES, FS, and GS, are used for operating system-specific things. So if you're going to be doing a lot of like reversing for a particular platform, like for example, I deal with a lot of Windows malware. For me, FS is valuable to know because there are a bunch of operating system contexts or structures that are pointed to or referenced off of SF. For example, like there's a bunch of anti-debugging tricks that you can find in different places within FS. So for me as a malware guy, that's valuable to know. Excuse me. So if you're going to be working with a particular platform, that's a very good thing to know for your platform. So these are the registers that we're going to talk about. Those are called the user accessible registers. So we've discussed the general purpose ones. Again, you can use these things for anything you can fit into them, but there are conventions. There are the special registers that I flagged off as EIP, the instruction pointer, and the flags registers. And then there are the segment registers. So we're about to move on to instructions. So does anyone want to ask a question here, or are you going? No? Okay, still going to take a break. Okay. So what we're going to get into now are instructions. So when you think of assembly language, when I showed you assembly language earlier, what I showed you was this. So at this point, we talked about how the processor works. We talked about, in particular, registers a bit. So now we're going to talk about the code that actually uses them. So hopefully you remember what this is. This is the hex representation of the main function of my hello world program. So again, I've broken each opcode up onto a separate line. I said I did that to make it readable, but I don't expect anyone to be able to read this because it sucks to have to read that, right? For readability's sake, again, each opcode is on its own line, but you still don't really know what they mean. This is where assembly language actually comes in. So you're correct that this is not assembly. The part that's assembly, well, those are the opcodes that assembly translates into. So you can directly program in them. And if you'd like to, be my guest, but you're not allowed to tell me how bad assembly is if you're going directly with opcodes. So on the left, we have the opcodes, which is what the binary is made out of, or made up of. And on the right, we have the instructions that actually make those things up. So I'm not sure if anyone here has taken a foreign language, or I guess any class, because this is not exclusive to foreign languages. But teachers often use these things called mnemonic devices. So I took Latin a long time ago. And our teacher kept saying this one thing. She kept saying, he was a rat. He was a rat. She keeps saying it all the time. Like in French, don't PC in the pool. Because in Latin, a rat means, I actually have a note of this, just because I don't remember all the tenses, but it means was. It was the third person past tense singular for is, meaning was. And it's kind of silly to keep saying, he was a rat, he was a rat. But all these, it's like double-digit years later now, that's like the one thing in Latin that I remember. So you can say it's silly, and don't PC in the pool. In French, PC means pool. So again, it's like, I remember a bit more French, but mnemonic devices work, and they're a lot easier than having to remember, for example, like the order of the planets, which I guess isn't that complex, but that's what a mnemonic device is. And we use them here in assembly. So opcode 55 directly translates to push EDP. And you might think, okay, that's pretty easy. But what you have to know is that I think 50 is push, And then the 5 part tells us what register we want to push. And that's still a pretty easy one. But after that, okay, move EBP ESP, 89 E5. I don't know which part of that is which, to be honest with you. I guess 89 is move, I have no idea. But the cool thing is I don't have to know, because that's where we have actual assembly language. So instead of having to remember the mnemonic, and like the base of the mnemonic, and then the proper opcode for your operands, we just have to remember the instructions. So what we want to do is push. So we say push. And the thing we'd like to push, and I'll explain the instruction push a little bit, the thing we'd like to push is in EBP. So we just say push EBP. It's a lot easier than having to figure out 55 every time. So just a moment of clarity here. So I hope that at least maybe one person like goes back to their room or home or work or whatever, like obj jumps something, or tries to look at some assembly. If you do, this is what I've been showing you. If you do, what you'll actually see will probably look like that down there. That's because a lot of tools, typically tools that you see in like Linux or GNU Linux, use AT&T syntax. Now what you have to know is that this is the same exact assembly. They're both dealing with the same instruction set. Everything is the same. It's a different visual way of displaying assembly language. There's some major differences, like in Intel, for move EBP ESP. Then if we look at AT&T, it's move ESP EBP. That's because the order of the operands are switched. You also see things like percent signs and dollar signs. It's the same code. And you can view any assembly in either of these fashions. Yeah.
I've always wondered, why did AT&T go with dollar signs and percent signs when Intel never gave them?
So it's weird. And I wasn't gonna. So like personally, I just use Intel because like that's just what I
Well, we use, yeah. But why did AT&T do that?
Well, so if you think about it logically, I guess it's kind of, it defines what's coming next. It's like you don't need to see a dollar sign to know that 0 isn't like an immediate value, and percent sign to know that EAX is a register. I'm sorry?
Yeah, I'm pretty sure it does.
Yeah, maybe. So that's the thing. Like, I don't know.
Yeah, I'm pretty sure it does. Which is weird.
Yeah, like maybe it's just more explicit in certain things.
Yeah.
I don't know. And again, I'm not trying to tell you one is better than the other because I don't know much about AT&T syntax. But what I do know is that
AT&T syntax is ugly. Intel is better.
so you'll start that kind of thing, right? It's like the console wars.
Right.
But I just wanted to show you this so you didn't like go home back. I'm gonna try this. I can do assembly, and then like disassemble something and see that and oh, what the hell is all this? So just know that's what it is. That's what you go home and you see. So I've got some good news and some bad news. I could have drawn this out to make it a little bit more dramatic, but I didn't. So there are about 400 possible mnemonics, and these stats are all from a Black Hat presentation from 2006, which will reference something that I'll reference later. But they found that there are approximately 400 possible mnemonics, which is a lot. But they also found that the top 5 mnemonics make up approximately 65% of code, which is a lot. And even then, the top 14 mnemonics make up 92% of code. So the number 400 can be really, really scary. But what this says to me is if you know a handful of instructions, you can read the bulk of assembly. And even if you can't make it through a function without like encountering a certain code you might not know, if you can tell how the bulk of it works and you can read about that other instruction in a manual or something, it really is pretty easy to understand. So this, I'm glad it was a stat that I found someone else using because I think it perfectly illustrates the fact that assembly really isn't that bad. So here are some basic instructions, and there are 1, 2, 3, 4, 5, 6, 7 here. And I'm going to teach you all of these in about 45 seconds-ish. And that's because I think, and again, maybe I'm wrong, maybe this entire thing, I am someone shaking their head.
No, you're right.
Okay, cool.
You're not wrong.
That was a good shaking the head, all right. It's typically as you know.
Yeah.
So yeah, 45 seconds starting now, I guess. So almost all of these instructions do exactly what you think they do. Except for move, which is a little deceiving. It's like it copies instead of moves. But as an example, we'll talk about add. In the syntax that we're using, Intel, the first operand is the destination, whereas the second is the source. So here if we had add 7, 3, it would take 3, add it to 7, and store the result in whatever the first operand points to. So it would leave 10 in the register that points to our destination. Subtract, very similar. And or XOR not, they're bitwise operations, and you have to know the bitwise operations. But if you know them, they do exactly what they look like they do. Except for move, which kills me, and I really should like take off this slide, because move leaves a copy of what it's copying, which can be a little deceptively named, but it's kind of funny that that's the most complexly named one here. And this is kind of the root of why I like assembly, or why I liked it at first. I still like it, but one of the first reasons was because you could see a line, and even if it looked really complex because there were a lot of them, you could see one line and know what it did. Like, it was pretty, there's not a lot of lying in assembly, which is cool. So a small problem is that that code would all run one instruction after the next, after the next, after the next, after the next. And real code doesn't often work that way. Typically, we have things like if statements or for loops or whatever. We have control flow modification. So we have the same thing in assembly. If you do a lot of programming in other languages, there's something you have to get used to, and that is the fact that, like, typically go-tos are frowned upon in other languages, or jumps. I challenge you to write any kind of assembly without a lot of jumps. Okay, that's what we do. There's a logical equivalent of a for or a while, but we do that like this, by using compares and then jumps. So I'll talk about some of those now. So does anyone know the terms minuend and subtrand? You do. I did not. I will be entirely honest with you. Like, I know the terms for things that you divide. This made no sense to me. So I actually had to Wikipedia this one once, put this slide together to find out what to call them. That's subtraction. That's subtraction. Fancy words for it, but again, I didn't know. But since I'm calling the arguments the different subtraction components, it kind of indicates to you that compare does subtraction. So the question then is, why not just subtract if we're doing subtraction anyway? That would be a good question, which conveniently has the answer on the next slide, because that's my question. And that is where the e-flags register comes back into play. So when you compare two things, the actual result itself is never stored. The arguments that you pass in are not actually modified. It just does a subtraction and stores some information about the results in the e-flags register. So here we're going to talk about two different flags. We're going to talk about the 0 flag and the sign flag. And these are used to, I guess, see some information about this is, I know people came in late, we started late, and I'm also the next presenter, so we're just going to go a little late. So the 0 flag and the sign flag. And they store results about the previous arithmetic instruction, or arithmetic instruction. So as an example, the 0 flag, it's a bit. The bit can be 1 or the bit can be 0. The bit is high, or 1, if the last arithmetic operation had a result of 0. So if 0 happened, the 0 flag goes high. Compared to that is the sign flag. And we're only talking about sign right now, just for the sake of day one stuff. For the sign flag, it's set to high, or set to 1, since it's a bit, if the operation would have resulted in a negative number. So by having this information available, we can make a bunch of logical jumps. Okay, so here an example of some things. So here's, I guess, the first assembly that we'll string together. My first instruction is move EAX, 7. So we place the value 7 into EAX. And then we compare EAX and 5. So again, this is subtraction. And the destination is the first register where the source is the second. So we're subtracting 5 from 7. This leaves us with 2. So 2 is not 0, so the 0 flag does not go high. And 2 is not negative, so the sign flag does not go high. So this tells us a bit about what happened in the subtraction. And the next example is compare EAX 7. So remember, compare does not change the actual what's in the register, so we're still comparing 7 to 7. So 7 minus 7 is 0. So the 0 flag goes high, and the sign flag stays low. And then we'll compare EAX, which is still 7, to hex F, 15. 15 is greater than 7, so 7 minus 15 is negative. So the 0 flag stays low because the result was not 0, but the sign flag goes high because the result was negative. So when we do these compares, and then we use particular jumps afterwards, we can do things like make while loops or for loops or if statements. There are a bunch of different types of jumps. So something interesting to show you here is I showed you the stat that there were 400-ish mnemonic devices. Lots of them are kind of derivative of each other. So here, these are all pretty, I think, understandable. There's JG for jump greater, JGE for jump if greater than or equal, JE for jump equal, jump, just always jump, it's not conditional, JME, jump if not equal, JLE, jump if less than or equal. There's tons of things that do what you think they do, but there's a lot of different instructions that might do something like that. So by following up a compare with a conditional jump, we can check the flags to then actually do what we need to do. So these jump instructions take one argument, and that argument is the location of where you'd like them to jump to if their criteria is met. So I'll have a little silent self-study time while I take a drink. trying to figure out what will happen here. Sorry? So I'll talk about this address in a minute. This is like a little reference to the thing. Okay, so that's where we're going. So the first thing that we do is we move 9 into EAX. So EAX now equals 9. And then we sub EAX 2. So we subtract 2 from EAX, which contains 9, which leaves us with a result of 7 in EAX. And then we compare EAX to 7. 7 minus 7, okay, the 0 flag goes up. And then we say jump if equal then. Okay, well, if two things are equal, the 0 flag should go up. So it checks the 0 flag. The 0 flag is high. So the condition of the jump is met, and we make the jump to the location. So I use 41414141 because it's kind of what you see in, it's like the traditional way of testing for buffer overflows. You jam a bunch of capital A's into something, and then you like change letters. 41 is A, yeah. And then you change letters around, but it's kind of like the proof of concept that you own something. If you can change EIP to 41414141, it kind of means like you've won the game. So that's why I chose that. So those are the instructions that we're talking about for now. I will talk about some that are memory specific in a moment when we get into memory. But we spoke about some basic instructions, just add, sub, move, compare. We talked about the eFlags register a bit and kind of used it some. And we talked about some control flow stuff, like compares or different jumps. So before we move on to memory and memory-related instructions, does anyone have any questions here?
Yeah.
Yes.
Back on that compare, was that compare conditional on the previous statements? So why
This-
did that jump work?
Okay, so this jump worked because what happened was, in compare, remember we do that subtraction,
Sure.
where we're not actually scoring the results.
Sure.
But that subtraction modifies the eFlags register.
Oh, you're comparing the, okay, gotcha.
Right, so what the jump instruction then does is it checks the eFlags register to see if the combination of flags that's set matches what it should be for the condition. So here, jump equals, the condition for being equal is that the 0 flag is high. So JE, yep, look to see if the 0 flag was high. And since it was,
Yeah. Then
7 minus 7 is 0, 0 flag.
So based on the previous thing, gotcha.
Right, yeah, based on the result of the comparison.
That's what, yeah.
Right. So jumps can follow things that aren't compares, but like typically this is what you see it end up doing. Well, so any other instruction question, bring on to memory. And memory is the last like technical bit of this part of the day. So cool. So memory and more instructions. At last I made memory, and memory is kind of the reason, I think I've given like 17 reasons that I've given this presentation. But memory is like really the reason that I want to do this presentation. Because I have a theory, and I don't know if it's right, but my theory is that if you can understand how memory works, the rest of the assembly is really, really easy. Again, I can be wrong, but my theory again is that if you understand memory, you can follow it and do something like the memory math, the instructions all will fall into place super easily. So understanding certain parts of how memory works is very, very important. Because it can also be very easy to get lost in memory. And maybe this is just my experience, maybe it's completely opposite. I don't know. So the question is, how is memory used in x86 assembly? Well, memory is important in any kind of programming, right? Even if you're not like directly, even if you're abstracted from it, memory is still a thing. But in x86, it's a lot more important, at least I think so, because you're not abstracted from it. So you have to deal with, I guess, the things that have to happen in memory in your assembly. So like in Python, when you call a function or create an object, there's lots of things happening in memory under the covers that you cause to happen, but you might not know are happening. In C, the same thing. Like when you make a variable or when you pass an argument, like you know what it's doing, but you know how it's happening? You might not. And if you're going to work with assembly, you actually have to be the cause of those things that are going to happen. So you get like a picture of like Sean Connery, like a You're the Man Now dog thing, because it's basically what it is. It's on you. That's why some people don't like assembly. So the first big thing that we're going to talk about, and the primary thing, is the stack. So the stack is a concept that's not unique to assembly. It's a programming concept that we see a lot. So the stack is this mysterious object, which I will have displayed out in a moment. It's what's called a first in, last out structure. So when you put something on the top and you put another thing on the top, in order to remove something, it has to be at the top of the stack. And I will illustrate that for you in a moment. A key thing to know, though, is that you can access values that aren't on the top. But in order to remove them, they have to be on the top of the stack. So again, I'll illustrate this, hopefully explain it a bit better in a minute. But before I do that, there are more instructions that we have to know to kind of arm ourselves to use the stack. So the first one is push. So when you push something, it places it at the top of the stack. And it takes the argument that you give to push is pretty sure it's always a register. Yes, it's always a register. It puts 32 bits on top of the stack. So interestingly, hopefully you remember ESP, the stack pointer, the thing that points to the top of the stack. When you push a value, it also subtracts, which is capitalized from the ESP register. Okay, so the instruction that counters that is pop. So where push puts things on top of the stack, pop removes things from the top of the stack. And it places it in the register that you give as an operand. And then it adds 4 to the ESP register. So you're back, you got another question. Excuse me, why do you add 4 to the stack pointer when the stack gets smaller? And that's a good question, and I think it's where a lot of the hang up about dealing with memory and assembly comes in. So here's my illustrated stack, which comes through clear, which is good. Here's my illustrated stack. So we don't have EBP here, the base pointer. Right now we're just looking at the top of our stack, which is pointed to by ESP. And the memory address of that is hex 1000. Okay, so we've got that set up right now. And then our first instruction here is move into EAX hex deadbeef. Okay, so far so good. So right now the top of the stack is the same as ESP, and we moved a value into EAX. And then we push EAX, and something happened here. First of all, it went onto the top of the stack, which is visually below feed food. And this is potentially the confusing part. That's because the stack grows downwards into memory. So the top of your stack will be at the lowest memory address. So this is why we subtract 4 from ESP, or the stack pointer, when we put new things on the stack. So again, this is what it looked like before. When we add a new thing to it, it grows into lower addresses. So the top of the stack is at the bottom of memory. And again, this is the part that can be a little confusing. So afterwards, we've just pushed a thing, we'll then pop a value out. So we pop whatever's at the top of the stack into EBX. And again, that happened to be dead beef, which is one of the things that you'll see a lot in people like to make words out of hex values for assembly things. And then we have feed food. So we push into EBX, and that removes the value that was at the top, that ESP was formerly pointing to, and puts it into the register EBX. It then adds 4 to the stack pointer to have it point at the top again. So the memory goes up, again, as we reduce what's in the stack. So hopefully this isn't too confusing, because this is one of the things that you really have to have a good grasp on if you're going to be working with assembly. Okay, so I'll stop for questions in a moment. Yeah. Stop for questions in a moment on that. So this is the last technical thing that I'm going to cover today for the sake of time and for the sake of day one. I'm trying to day one stuff, I guess. And just know that you've just sat through basically a semester of assembly. So when I say day one, I don't mean day one of class. I mean, certain things you have to cut out. Okay, so the last technical thing that we're going to talk about are pointers and data types. So in higher level languages, you have these notion of data types. Whereas here we really don't, and I hope to illustrate that here. So here we move hex 1000 into EAX. And hex 1000 is the address of the top of our stack. It's the address that points to feed food. Then I move EAX into EBX. So the question is, what got moved here? So what actually ends up in EBX is hex 1000. We moved the address of the value in memory, but we didn't actually move the value. And that's where this whole idea of pointers comes in. Because again, assembly does not know what you mean to use data inside a register for. You could put whatever. I'm not going to scroll back. Before I had 41414141 in the IP, right? As far as assembly is concerned, that can be anything. That might not be in the legal bounds of memory for this program, but assembly doesn't know. Assembly doesn't care. And that's because it's kind of on your shoulders to manage. So what we've done here is we've just moved whatever this random raw data is that just happens to look like that memory address. Now, if we'd like to actually interact with the memory, that's where the idea of hierarchy comes in. And this is not a concept that's unique to assembly either. But what we do is we put brackets around a register to say, I'm not talking about this value, but treat this value like a memory address. So in EAX, here is hex 1000. So what I'm saying here is don't move EAX, move the value that EAX points to. So that's what we're doing. So here we end up with hex feed food in ECX. So that's something that makes sense? Cool. I'll give you an opportunity for questions in just a second. But this is absolutely critical to understand if you're going to be dealing with reading or writing assembly. Because you have to know when you're dealing with the value that you actually see in a register versus the value that it's pointing to. So if you can get a sense of how the stack grows and how to access it, I think the instruction will really, really fall into place. And again, maybe I'm wrong. But that was kind of the impetus for doing the presentation. Just to say if you can get memory, the rest will just happen. So this is what we're almost done with this presentation. But this is kind of the recap of memory. We've spoken about what the stack was and the registers that are used to manage it, EDP, the base pointer, and ESP. I didn't talk too much about EDP, unfortunately, but for the context of today, ESP is what was important. Then we talked about how to use things as pointers and how to dereference things. So we're about to go to a wrap-up. Does anyone have any questions here? Cool. So I had a few goals for today's presentation. I wanted to kind of explain, A, what assembly was, where in the chain of things that came in, why I think it's worth learning, and a bit about how it works. But when I initially sent the email out to DC404, I promised again that you would not know assembly after you left. Because again, it wasn't really, if you do, that's awesome. That's even more awesome if you didn't know it before you showed up. But what I wanted to do is kind of give you some kind of understanding and foundation, and then some really good next steps to go to if you're actually interested in doing. And it turned from next steps to next step. Not for lack of things, but for the fact that the consensus for me was totally, there was nothing else that was worth mentioning for an introductory assembly thing. So there's a really cool website, I'm not associated with it at all, OpenSecurityTraining.info. They do a bunch of trainings and courses and all sorts of cool stuff for different security-esque topics. Some of them are specifically incident response and Wi-Fi hacking. Some of them are malware analysis or intro to x86, intermediate x86, advanced x86. And then on top of that, all of that, reversing is a separate course. So they really go into things. And the courses, I've looked at a couple of them, are awesome. They're all free. They are not courses that you go to them. They're just materials you can download. So the intro to x86 course, I think it had 12 hours of video. So the guy who put it together, I think it was Zeno Kova for this. He works at MITRE up in Boston-ish. And it was a course that he gave internally, and his company allowed him to record it and put all the materials online. So it's a really, really good course. That's fantastic. It's got slides, it's got labs, it's got videos. It covers everything I did in more detail, and then things I didn't. So if you would like to go into assembly, this is it. Seriously, do it. I went through it. I found it awesome. Worth doing. And also at the end of it, there's this thing called the Bomb Lab. It's not something he made. It's something he sourced from an old Carnegie Mellon lab or something. But it's worth doing, seriously. Even if you think you know assembly already, do it. If you do the course, don't skip out because you finished the material. Do that final lab. So that was this presentation. Again, my name is Brian Tanzi. If you want the deck, it will be on, you don't know what my website is, you can email me, I will tweet it, or I will put it in SE2600. I will try and make it available.
It's on your session information on the PhreakNIC.info website.
Okay, that points to a slightly older version. That points to the one I gave at DC404. So it references DC404, but it's effectively the same content. And there's tons of presentation notes. So cool. Thanks. That was this one.